Boom. And then I could even hide that because I know Isabella's going to hate this bar on the top. Boom. Gone. All right, let's do it. I'm excited. You excited? Let's do it. I even took my sleeve off, right? All right, here we go. Hello? Here we go. Try some. We did this, yes? Yes? Hello? We did this, yes? Hello? Am I? Okay. Polyprotic. Yes? No, we're gonna cover it, right? Yes. Let's go. Polyprotic acids and bases. Poly means what? More than one, right? So that means protic sounds like what? Protic. Pro what? Protons. Polyprotic must mean more than one proton. Oh, that's it? Yeah. So polyprotic means more than one proton. So it means more than one proton is what polyprotic means. Okay. There are other terms, by the way. There's also called amphoteric, right? I don't know if you're going to see it. I don't think Regents covers it, right? It's not the same, right? But I think polyprotic will cover, right? But the likelihood of seeing this on Regents is actually quite low, right? But I'm just trying to tell you in case they throw a curveball, okay? Let's do it. So monoprotic, diprotic, triprotic, right? If it has two wheels, it's called a what? A dicycle. So diprotic must be two protons. Tricycle has how many wheels? So therefore triprotic is three protons, right? Right? So diprotic and triprotic are both polyprotic acids. Okay? Diprotic and triprotic are both type of polyprotic acids. So polyprotic come in two flavors, right? Diprotic and triprotic. And if you're thinking, hey, Mr. Kim, what about something that is got more than that? Like, could you have tetraprotic? And the answer is no, not really. And the reason is because of this, right? Let's think about this, right? If you have, let's say, Stavro, who seems bored, found the wall more interesting than what I'm saying. That cuts deep, man. All right, try to focus here. So if Stavro is HC, let's say H2SO4, right? If Stavro is H2SO4, let Windows access your location. No, stop spying on me. All right, so if that's Stavro, right? Then would you say Stavro is a monoprotic or polyprotic? Poly, because why? He seems to have more than one proton, right? Specifically diprotic, right? Now, let's see. You know that Stavro is going to give up a proton because he's an acid. See that? Now, they don't all fall off at once, okay? So imagine, in his left hand, he's got a proton. In his right hand, he's got a proton. Got it? So that means that he's going to give up the proton in which hand? Left or right hand, Stavro? So he gives up the proton on his right hand, and then, can you see it's SO4, right? Now, fine. God, you guys are like so, no, Mr. Kim, I see an S4. What are you trying to write? What happened? You guys wake up on the wrong side of the bed or something then? H2SO4. You're never satisfied with anything in this class. Well, joke's on you, right? We were never satisfied, period. Right? All right. Here we go. Is that better, Stavro? All right. So now, would you agree that because he gave up a what? H plus, remember, not H plus, that he'd be a negative charge, right? We even did something here that I didn't do in the other class, which is Lewis, right? Right? Lewis picks up a negative charge. All right. So anyway, negative. Now, you guys remember from redox? Remember what I remember from redox, right? Now, he is polyprotic, which means what? He can give up a what? The proton that's in his other hand, right? But if that were to happen, then you would end up with this. would now have to give up yet another proton, and then would be SO4, what? SO4 minus 2, right? All right, now think about this. What? Okay, so in the first deprotonation, I go up to Stavro and I take his proton from it. Guys, she has to go because she's a dichloromethane. All right, have fun. Is that your poster?
No, it's been in there for weeks. It was in Max's desk for a while.
Well, do me a favor, kids. If you're gonna make a cheat sheet, try to make it smaller than this, right? Obviously, this kid, right? This is the biggest cheat sheet ever. What? There's an ogre. Ogre. Ogres have onions. Onions have onions. Onions have layers. Ogres have layers, right? Ogres have layers. Onions have layers. Atoms have layers of orbital shells, right? All right, so moving on, right? Let's go. All right, so what are we talking about? So Stavro, right? Diprotic. And what happens? First proton. First of all, H2SO4. What's the charge of H2SO4? H2, right, what? H2SO4 is what charge? Neutral, no charge, right? Now, if I go up and tell him to give up his plus, H plus, he's okay with that. But once he gives up that H plus, now what is he? HSO4 minus. When I ask him to give him a second proton, you want to, but is it as easy?
No.
Why not?
Because of force of like attraction.
Right, because opposites attract, and because after the first proton pops off, you become more negative. So therefore, taking another positive thing away becomes more difficult. This is why you don't see tetraprotic acids. As you keep popping protons off, the acids become more and more negative, which means that there's no way on God's green earth you're going to be able to pop that fourth H off, because now it's so negative, it's going to hold on to its positive things. Everybody understand? So this is something that was asked eons ago. So diprotic, triprotic are probably the end, right? Now, as far as regions is concerned, your this does not happen. All right. As far as regions is concerned, H2SO4 does this. Right? Does that, and you have to balance. This is regions. But according to regions, this is how H2SO4 deprotonates. That's how it gives up protons. Because it's diprotic. But it's actually wrong. When you get to like honors or honors, you're supposed to cover on honors, but if you get to AP Chem, you understand that polyprotic acids pop off one proton at a time, and every time it happens, the likelihood of it coming off gets harder and harder, and therefore you're thinking, Mr. Kim, that's so cool. So we discuss it. No, we calculate it using numbers, right? Again, I keep saying that because I don't want to see you. Like I've had kids who come to me like, Mr. Kim, the whole like, oh my gosh, right? They're like this, right? And then they'll come to my AP Chem class, and then they're like, what? And then next thing you know, I don't want to walk down the stairs in front of them in the hallway because they're probably going to push me down, because they're like, I thought AP Chem was going to be Mr. Kim season 2, but it's literally more like math class season 3, right? So if you're ready for that though, right? Then come to AP Chem, right? If you're ready for that. If you're like, I really want to apply math towards this, right? Then you'll be fun. You'll have fun. But if you don't want to do it, you can't do it, right? It's a different class. All right, calculation of pH. Here we go. So what is pH? All right, anybody know what pH is? Have you heard of pH? What is pH? Go.
It measures the substance acidity.
Yeah, acidity or basicity is what you will say if you live in the United States. But we also say stupid things like soccer, right? Right? Whereas everybody else in the world, it's what? It's football, right? Anyway, so everywhere else in the world is acidity or alkalinity. So if you have parents or grandparents that are foreign and they did cover science sometime in their life, they will understand alkalinity, not basicity. Basicity is first of all, it sounds stupid, right? Basicity, right? What is that, right? So, but we do say basicity, right? Right? But when you get to college, we don't say that anymore, right? We say alkalinity. So it's acid or alkaline. Oh, you mean like alkaline earth metals? Oh my God, wait a minute. Wait, why are they called alkaline earth metals? Anyone know what alkaline earth metals are? Group what? Group? No, one. I'm sorry, alkaline metals. Oops, did I? Alkaline metals are group one. That's what I meant. Don't hear what I say, hear what I meant. All right, so group one is alkaline metals. Group two is what? Alkaline earth metals. Why are they called alkaline metals?
For alkaline.
They're basic. Why is it basic? Wait, I have to do this. This is
Less protein.
I'm gonna write in different color, right? But this isn't part of the notes, so don't worry about it, right? Check it out. Give me a poster child of alkaline metal. Na. What happens when you throw Na into water? Yes, but it's a little bit more than stronger than dissolve. It what? Blows up. Boom. Right? It blows up. Now, ready? Oh, this is good. This is good. Right. Hold on. I gotta get my reference table out. I gotta get my reference table. Oh my goodness. Right? There we go. Reference table. I got mine. Have you got yours? Oh my. Okay. Yo, check it out. Ready? Right? What does this look like it's gonna be? What kind of chemical reaction? You see one element and you see a bunch of guys coming to a dance. What? Single replacement. We go to table what? Oh, let's go to table J, right? Oh, here we are, table J. Let's go. You got sodium, right? Where's sodium? Way the heck up here, right? It's way the heck up here. Now, sodium is what? Tendency to form cation or anion?
Oh,
What? What? I'm yelling because it's on video. I don't want people listening to it like, oh my God, the kid in the mic said anion, right? Now, ready? Do you understand that the people watching this video 30 years from now, right? Right? They're gonna be laughing, right? It goes, oh, somebody said, right? But they're gonna say, oh, come on, guys, don't be mean to the kid. He at least corrected himself, right? Sodium has a tendency to form what kind of ions? Cations. So therefore, going back to this, what is it gonna try to knock off? H or the O? H. Okay. So let's go. Where's H? Oh, it's all the way at the bottom. So therefore, will sodium be able to knock an H off? Yes. Let's do it. So let's do it. So if sodium knocks off the H, right? Then it's going to get a what? Sodium is going to now pair with who? Not oxygen. Oh! Oh my gosh. What happens? Wait a minute. And then when you have two H's, what happens? They mingle together and form. Remember, you can't have H's by themselves. Oh my God. Right? So, right? So what happens? You get sodium in water, creates two sodium hydroxides and hydrogen gas. So you put Na in water, and what do you just create? Sodium hydroxide. Hey, what is this? It's a what according to who? What? It's an Arrhenius base. Oh, that's why they're alkaline metals. Alkaline metals are metals when you drop into water, turns the water bitter and alkaline, turns it into base. You want to create a base? You can just grab an alkaline metal and drop it into water. Instant presto, base O, right? Dangerous, but it'll do it, right? But that's why it's called alkaline metals, right? Isn't that awesome, right? I don't know. I was one of those kids in high school. I'd be like, "Oh my God!" And I go to my math, the chem teacher. I'm like, "Oh my God, Mr. V, is that what happens?" And then what did he say? Yeah, that's what happens, right? That's how we talked, right? And then I was like, oh my God, that's so cool, right? And he's like, yeah, it's kind of cool, right? He didn't like me. All right. Anyway, what?
What happened to alkaline earth metal?
Ah, let's go. Alkaline earth metal. Magnesium is an alkali earth metal, right? Plus H2O. What happens? Well, where's magnesium? Oh, it's up here, right? Will magnesium knock off hydrogen? Of course it can. So it's going to be Mg. Oh, is it MgOH though? Magnesium is that group 2, so therefore it's Mg plus. Right, so it's going to be what? Parentheses 2. Remember crisscross drop charges, right? Yeah, you're thinking, oh my God, Mr. Kim, I have to remember this, right? Oh, look at that. So does that also create hydroxide? Yes, it does, right? Cool, right? Now, why it's called alkali earth metals? I have no idea where the earth comes from. Because, oh, Mr. Kim, because it's found on earth. So is everything else, right? I don't know. I don't know where it's called earth metal, right? But I have no idea. I don't, and I don't care, right? All right, so that's kind of fun. That's a little fun segue, right? All right, so let's go. pH, right? So pH, right? Arush said, it tells you either something is acidic or basic, right? Everybody agree? Yeah? Everybody remember that? I have a question for you. Any of you guys who had bio last year, did any of you actually stop class, raise your hands, goes, why is it P and an H? Where does that come from?
Is that not height? Oh, I thought
Oh, is that what they tell you?
that's what they tell us.
Who?
It's a great thing.
Oh, God, I feel so bad.
I think said that.
Fake news. It is wrong. Wrong, wrong. So wrong. Can't be any more wronger than wrong. It's not percent of hydrogen. Nobody knows?
That's right. That's what I was.
Oh, so you're telling me that I don't know this either? Right? First, you're staring at the blank wall. First, you think the blank wall is more interesting than what's coming out, the words coming out of my mouth, right? And you're down telling me nobody knows. What? Power of hydrogen. That's what it stands for. And some of you guys who are okay with math, who didn't have traumatic mathematical experience like Mr. Kim did, you're going to actually appreciate this because I was like, wait, why didn't my math teacher explain this? It's called power of hydrogen, okay? It's called power of hydrogen. I don't understand. Doc, he got his PhD at NYU. And I looked him up. I think he finished in 98.
Believe him.
He got his PhD in 98. You know when Mr. Kim started? Wait, when did Mr. Kim start his PhD at NYU?
04.
99.
Oh,
When did Doc get his PhD? 98. And I was like, wait a minute, right? I'm guessing we probably chewed some of the same dirt at NYU, right? And I asked, I was like, who are some of these people? And then he's like, I don't know. I worked with people. I'm like, wait, I'm dying to know who he worked with because I know like every single scientist there too, right? I was like, whatever. All right, moving on. Power of hydrogen is what it stands for, right? But then you know what? I wasn't a good science student. You know that, right? I mean, think about it. I'm like ADHD, right? ADD, right? Remember, I just went off topic because of alkali metal. I was like that in my grad school classes too. I was like all over the place, right? Making all these connections. That's why I did poorly in my classes, but I rocked in labs. That's why professors are always asking, like, can you work in my lab, right? But moving on, right? Power of hydrogen. All right, here we go. That's what it's called. What does that mean? I don't know about you. I see like Power Rangers when you hear that, right? It's not. Here we go. So it has to do with this, right? But what does it mean? It means this. When they say power, it means, right? Power as in exponent, right? You know that. You've heard like raised to the power of. You've heard that term in math, right? You're right. 2 squared is 2 raised to the power of 2, right? That's where the word power comes from. Meaning, not only is it a power, it is also base 10 understood. Which means because they didn't mention any bases, it's a power of a base 10 number. Or, in other words, exponent of a base 10 number is what log is. And that's what the P is. Yes?
Higher go on page more hydrogen.
Yeah, but you remember, I don't know if you've seen the equation. Equations are negative. Why? Because we don't work that way. We work with negative exponents. Okay, so let me explain to you in a second what happens. All right, so ready? Here we go. So all this could be done. Me telling you, like, remember this equation. You really need to remember this equation if you don't, right? But you've seen it in bio, maybe negative log of hydrogen concentration, right? Right. You're supposed to, right? Anyway, it doesn't matter, right? I used to cover them on a teach bio. All right, so here we go. Right, so now what happens? And to be fair to Miss Joe, I also don't explain to them what a power of hydrogen is when I taught bio, right? Because it's more fun when you get to chems, like, hey, you know what? Remember pH, right? All right, so here we go. So now you have that, right? So think about this. What does that mean? Well, the P means power or exponent of a base 10, okay? So again, the P means power of and base 10. What does that mean? That means when you have something like a POH, right? It means it's a negative log of OH, except it's not OH, OH minus, right? So it's actually power of hydrogen ion, right? Not hydrogen, right? But let's face it, biologists are stupid. Well, I can make fun of them because I'm a biologist myself, right? And they don't really understand chemistry, right? As well. So if you take if it's a P orange, it's the negative log of what? Orange, or the concentration of orange, right? If it's what's that? Negative log of Trent. How do you even do that? I don't know. Maybe do negative symbol, log, and then go to alphabet mode, type in Trent and hit enter. Who knows? But whenever you see the lowercase p in front of a number, it means you replace it with the negative log, right? That's what it means. Got it? Now, how do logs work? Right? Log seems like it's a complex thing, but it's not. So let's think about how log works, right? Yeah, let's talk about how log works, right? So you remember I said base 10, right? So if you take a log of a number, for example, right? Log of 100.
How many 10?
Yeah. What power do you need to raise 10 to, right? That means what it's asking is 10 raised to what power equals 100, and the log of 100 is going to return that value of the x. That's what a logarithmic function is. Don't overthink it. So in that case, 10 raised to what power will give you 100? 10 times what? 10, how many 10 squared, right? Right? Do you agree? Right? So therefore, log of 100 will equal number 2. It's that easy. Everybody okay? Now, it goes the other way. If you go to log of 0.01, right? Then what happens? Well, you can change this to a exponent, right? Log 10 times 10 to raise to what value will give you 0.01? Minus how many times?
3.
1, 2, 3, right? Everybody, is it? 1, 2, 3. Right. Okay. So it's 3 times, which means that the answer would be minus 3. But because we work with negative exponents, that's what I just told you, that's why we put a negative in front of the pH. Okay. All right. So this is going to bring up something interesting. If you understand this a little bit, when you do regions and you come across pH calculations, some of them you can do it without a calculator. Okay. All right, here we go. So keep that on back burner. Let's go into pH scale. pH scale runs from 0 to 14, where 0 is acidic, 7 is neutral, 14 is basic, and you got to memorize this. Okay? You got to memorize that. So what does that mean? pH value, can it be higher than 14? No. So that's why I came across an interesting meme last night trying to fall asleep. And then some kid had it says, when your calculation in chemistry is doing great, and then it says pH equals 17, and it's a screaming person, right? And he goes, I don't understand. If someone explained this, and then somebody said, oh, that's because pH can never be 14. What do you think Mr. Kim did? I responded. I said, well, actually, it can be greater than 14. But if it's greater than 14, it means something else is happening with the water. And I went into this. I wrote like 3 pages worth of reply, right? You know what they're thinking, right? I'm going to get downvoted because I'm like, dude, I just want, right? But as far as Regents is concerned, 14 is the max. Okay. Here we go. So something like vinegar or lemon would have a pH that is what? Not close to 0, definitely what? Less than what value? 7. Because what kind of pH is it when you're 0? What kind of solution are you when you're 0? Yeah. If you have something at a pH of 0, could you put it in your salad? You could, except your salad would be gone because it'll dissolve the salad, right? You understand? Right? What a pH of 2? Could you put that into salad? Yeah, if you want liquid salad. So what is like vinegar? It depends. It's like a 4.8. However, pH is not the best scale, right? And that's why in AP Chem we use something else that we'll never cover here, which is what I went into in my response too. Equilibrium constant of water at different temperatures and Kw and Ka and Kb, and I'm going to explain all that, right? Love to see. I love doing that just to troll people about how stupid somebody is. Hi.
You had a negative log, so does that translate to your answer like log of the one?
It'll always be positive. You'll see in a second why. Okay. All right, here we go. How does pH work? pH is really looking at how much hydrogen ion is in a solution. Okay. The pH is literally just describing to you how much hydrogen ion is in a solution. All right. So let's look at HCl. It is a strong acid. We know that. Strong acids, 100% dissociation, right? Again, you got to remember that, right? If it's strong acid, all of it dissociates into ions, right? Which means if it's a strong Arrhenius or Bronsted acid, all of the protons will be ions. Okay? See that? So you get, right? You start. If you start with where am I at? I lost my slide. Sorry. It doesn't matter. If you start with, let's say, 100% and none of it here, right? At the end, what does that mean? How much percent of HCl you have left over? 0. It's all gone. And then what would happen? You have 100% of these two. You understand what I'm saying? All right. In other words, I can change this percentage with molarity. If I end up with, let's say, right, I don't have space here, so maybe actually I can do this, right? The other thing I could say is, instead of percentages, I use molarity, right? So if I use, let's say if I have, dang it, 10 molar and 0 molar here, right? Because we don't have any in the beginning. Then at the end, how much of HCl we have left over at the end? 0 molar. But how many of these? It's going to be 10 each, not 5 each, right? Remember, we're not splitting the concentration, right? It's 1 to 1 to 1 ratio. Everybody okay? That's stoichiometry, right? Some of you guys are now writing, oh no, go review stoichiometry, right? Should I need to review stoichiometry? Yes, you should, right? All right, let's go. All right, so let's go. So if we have HCl at 0.1 molar, then we know 100% will turn into H plus and Cl minus, so we end up with respectively that much. However, we don't care about this guy, right? Because how much does that affect the pH? Very little, because remember, HCl, strong acid or weak acid? So what's Cl minus? It's known as a what? Weak, what kind of base? No, but it came from HCl, strong, it came on acid. So what kind of bases are those when it
Conjugate.
conjugate? Weak, it's a weak conjugate base, right? So weak conjugate base. Weak acids or bases cannot change pH. You understand? Right? pH is governed by strong guys. So therefore, we don't really care about this so much. So we really don't care about this so much, but this does matter. Okay. So what does that mean? Moving forward, if they give you a concentration of a strong acid, it might as well be the concentration of the H plus. That's very important. If you get a concentration of HCl, they might as well just tell you it's the concentration of the H plus. Why is that important? Because we plug that into our pH calculation, right? So remember, 0.10 molar of HCl also contains 0.10 molar of H plus. So therefore, plugging it into the pH calculation, you can directly plug that value in, knowing well that all of that acid will turn all of it into the same exact amount of H plus. You got me? All right. This one is easy. You could actually do this without a calculator if you want to, right? You can do this without a calculator if you want to. Let's check it out, right? Bless you. Obviously, positive or negative exponent? Negative exponent. How many places do you need to... Oh, I screwed this up. It's not 3 places. Because I messed up, guys, right? I got so excited I messed up. Because remember, Mr. Kim skipped it. You got to write it in what? Scientific notation. Okay? And then this means what? How many places you move from the 1, not from the 10, right? From a 1, how many places you need to move to get to 0.1? Yeah, it's going to be point minus 1. Right? Everybody thank Jeet for blurting out. Right? So in the previous example, I'm going to go back and change it only because I don't... Oh, I erased it. Oh, good. I erased it. That's terrible. All right, ready? So therefore, what happens? If you plug this right back in, pH equals negative log, right, of 1 times 10 to the minus 1, right? And this I did properly in the other class. Log of 1 doesn't mean anything. Log of 1 doesn't mean anything. So it might as well be written as negative log of 10 to the minus 1. Does anybody know what log of 1 is? It's how many 10s will go into a 1? 0. You just said 0, right? Yeah, so it's 0. Log of 1 is 0, right?
10 to the minus 1
10
is
to the
1.
minus 2.
Hold on. 10 to the 1 is 0. So that's why we're just doing log of 10 to the minus 1. 10 to the minus 1 would be what? Right? 1, because log of 10 to the minus 1 would be minus 1, but there is a minus, right? So therefore, if I color code this, this is what happens. See this minus, right? It'll give us a value that looks like this, right? pH is 1, okay? So, right now, one more thing that I don't think Regents care so much about, right? Which is this. Sig fig rules. There's a new sig fig rule that you want to add if you want to do logarithmics. This is not a math thing, it's a science thing. In logarithmic, the number you take the log of, the number of sig figs is equal to the number of decimal places in your final answer. Okay? So, what?
It says 0.10 equal to 1 times 10 to the negative 1. 10 to the negative 1, then it's just 1. Yeah, well, then that should be 1.
10 to the negative
No,
1?
1, if it's scientific notation, like not scientific notation,
And then raise second.
1 times 10 to the negative 1 is just 1.
Yeah, then double negative.
It's supposed to be to the negative 2.
Why don't you take a calculator, right? Before you say that. Somebody, yeah, take a calculator, put in 1 times 10 to the minus 1, hit enter, and tell me what you get. 1 times 10 to the minus 1?
This
No, not log. Just do 1 times 10 to the minus 1. Tell me what you get. You don't get a 1. What do you get? Yeah. Right? So you take the log of that, then you get 1. I don't know what you're trying to say. You're trying to correct me, but I'm trying to tell you
No, I'm just asking.
what?
Yeah.
Huh?
Isn't scientific notation each decimal point for one exponent?
Okay.
So aren't you moving 2 decimal points?
How many sig figs? The answer has to have the same decimal. Oh, so it's you're saying point what? So what's your answer? So in fact, if anything, it should be what? 1.00, because it's the number of decimal places. Right? I'm trying to explain to you, it's a new rule that you've not seen. Okay? So I don't understand what you're trying to refute here, because the math is correct. And I think for the people who are watching the video, you're just confusing everybody because you're making it seem like there's a mistake here. There is no mistake here. If you see a mistake, there's no mistake.
No, just ask them. Confused, otherwise, yeah.
What do you mean? What are you confused on? Because you're assuming that you're actually moving a decimal from a 10. Your math is flawed right now. Okay? Right? You're moving, right? And literally, I've been telling you 10 to the 0 is 1 because log of 1 is 0, and you're refusing to listen to me on that. And then now you came to the same conclusion that I've been telling you to try to tell you that you're wrong, to tell me now you're right. So again, guys, please stop, right? Let's follow the notes, okay? Right? I mean, I welcome you trying to think about it, but at the same time, dude, one other thing is, if as a scientist or a science student, if somebody tells you you're wrong, instead of immediately going to defensive mode to defend yourself, what should a scientist do? Accept what you've been told and then see if you disbelieve what they're telling you and try to prove your disbelief, right? That's what a scientist does, right? A scientist, when it's told something that is wrong, that you don't believe in, you try to disprove why you don't believe it. And if you can't disprove why you can't believe it, you have to accept it, right? Yep. All right, moving on. Sample. Oh, look, I gotta delete this. All right, hold on. Keep this. I want to keep that, but oh no, sharing is stopped. Don't stop the sharing. I want to go back here. Hello. Do that, and then go back to sharing. Video still rolling. Good. We are still recording. Good. And if I do this, that's good. All right. And let's do sample problem 19.2. Sample problem 19.2 says, what is the pH of solution with a H plus concentration of this? This is like, again, don't overthink it. Okay. So the other thing is, if you don't understand the logic, just use a calculator. Okay. Right? It's not worth sitting there trying to say, look, you know what, that makes no sense. Because look, if it makes no sense to you, use a calculator. And if the calculator agrees with you, then you're right, I'm wrong. If the calculator disagrees with you, then I'm sorry, you're wrong and you're misinformed. At which point you need to abandon that, because what's happening is you're going to confuse yourself and everybody else. So that's a question. All we have to do is literally just plug it in. Hey, am I going to do this in my head? No. However, in the old AP, up to 2 years ago, you would have to try to come up with this in your own head. It's not impossible. You can do it, right? What you do is you take a log of 2 numbers that are between that encompass this number, and then get their values and then guesstimate off of that, right? So AP used to be much more difficult, because did you know they didn't let you use a calculator in AP? Right? Can you imagine doing all of this and you don't get to use a calculator? You have to do this in your head or on paper. That used to be AP. Starting last year, they allowed calculators, but it doesn't make it, and it actually makes it more complicated, right? All right, moving on. You get one of these, all right? But what do we say? the rule is the number of sig figs is a number of decimal places. So therefore, what should your answer be? 9.3. Yeah, except you got to stop here, right? Which means what? 9.7, 9.38. Good. Okay. So hold up, right? This is two significant figures, therefore 2 decimal places in your answer. Now, is Regents gonna come after you for screwing that up? No, no one cares. In fact, when I do go over this in AP, none of the students from honors seem to actually even know this. Right? What's up? Yeah. All right. So here we go. You got your own time. Go. Let's do it. Can you do that one and that one? Ooh, one of them can be done without a calculator. Actually, both can, but one of them could be much easily done without a calculator. First one should take no time. I wish I can pause this. Can I pause this? Can I pause you? Nope. I just opened the chat. I should talk to myself. I'm gonna try to figure out the pause. Is Alt key. Oh, that makes sense. So if I do this and then go Alt P for unpause. Now I'm like OCD, so I have to check to see if it's actually recording. It's going, I think. All right, so all I know, it could be that I just killed the recording, but that's okay. All right, let's go. First one is what? Let's go to a different color because, oh my God, that's not what I want. Help. Okay, first one, let's go to a different color. Negative log of 1 times 10 to the minus 4. All right, you ready? What is that? It's simply going to be what? 4. How many sig figs? Yeah, it's just one decimal. It's no decimal place, 1 sig fig. So that's the correct answer. Let's go to this one. Could you do this without a calculator? You could, but I wouldn't do it. That's how you would set it up, right, guys? All right, now, Gabriella, I see her moving calculator. So, do you have a value for me? No. Come on, somebody. Give me. Press negative. Press log. Press 0.0015 and hit enter. Go. Somebody tell me. 2.8. 2. 3. 9. Oh. Okay, stop. All right, so now, what's the answer? How many sig figs do you see here? 2 sig figs, so therefore 2 decimal places, so it should be 2.82 should be your answer. Okay. Now again, if you're not sure, if you write 2.8 or 4.0, I think on Regents for your response, they're not going to care. Okay. But if you want to know the rule, that's the rule. But do me a favor, on a day of the Regents, don't freak out, or on my test, don't freak out and be like, oh my God, I forgot the rule. This is going to screw me over. I will not penalize you if you write pH with the wrong sig figs. Okay. As long as you don't put like 3 instead of 2.82. Okay. So if you put like 1 decimal place on a pH, I will allow it. Got it? So if you put 4.0 or 2.82, acceptable. If you put 4.00 or 2.82, I'll accept it. But if you put 4 and 3, I'll only accept the 4. Got it? Moving on. How is pH related to, I can't see, POH? All right. So you guys, there's a pH. There's also a POH. Why? You didn't say POH in bio, but where there's pH, there's also got to be POH, right? So how are they related? In a same solution, pH and POH should always add up to number 14. And I put information here that no Regents Chem cares about, which only dealt with in AP Chem. When they say that, it's at 25 degrees Celsius. Regents will never ask you a question that's not at 25 degrees Celsius. In fact, even AP, they don't ask you. When they say pH and POHs, it's always assumed that it's at 25 degrees Celsius, okay? That's the long post that I put in this morning on Reddit that people are going to probably hate me for, right? All right, so what does that mean? All right, so what does that mean? That means sample problem 19.4. That's what it means. If they ask you what is the pH of solution if the hydroxide concentration is this, how would you ever solve that? You can't plug this into negative log and get pH because we're not solving for pH. We got OH minus concentration, right? So what that means that we can't get the pH, but we can calculate the POH. Are you with me? Yeah, what's up? Yeah, that's literally what we're gonna do. All right. So ready? How do you figure out POH? POH should be negative log of what? OH minus, right? So if you plug that value, I don't know why I added a 0. Bad, Mr. Kim, right? I changed the sig fig. That's a no-no, right? But that's okay. All right. Remember, I told you I don't care about the sig fig so much on pH. All right, so you do that. Would you do this in your calculator or by your head? Let's use a calculator. Somebody do this and tell me what you get. Right? This is practice, man. Negative log parentheses 4.0 times 10 to the minus 11. Right? Hit enter. By the way, be careful. Those of you using graphing TI calculators, not allowed on regions. The one that Kevin, hold up your calculator. You got to use one of those. My concern is, depending on what kind of calculator you have, the logarithmic entry, it's like different orders of key presses, right? Just be careful. Okay. All right. So what do we get? 10.397. Sounds close enough, right? Good. 10.40. All right. Everybody okay? How much you want to bet if this is a multiple choice question? One of the answer choices is 10.40. And what's going to happen? The kid just punching away in the calculator will notice that that's one of the answers. They'll circle it, except they're asking for what? pH, not POH, right? So what did Arush say? How do you get the pH from here? That's right. 14 minus that, which should give us something around the neighborhood like 3 point something, right? 3.6? Yes, 3.6. Okay, yeah. So again, that extra 0 is extraneous. That's wrong, but that's okay. I don't really care about sig figs too much on a pH calculation. So here's an interesting point. If this is a multiple choice question, in your answer choice, it'll be like A, 10.40, B, 3.60, C, 7.0, and D, 14, right? Right? So be careful. Just because you're punching them in a calculator mindlessly, if a number happens to pop up as one of the answer choices, that's not the correct answer. You got to make sure the work supports the answer. Okay? Questions, comments, concerns? Don't forget to hit the like button. Here we go. Indicators. All right. So now that's it. As far as pH is concerned, all you have to do is you just have to punch in the value of the H plus and you're done. Or if they give you OH minus, plug in the value, hit the answer, and then subtract it from 14, and you're done. Or vice versa, okay? Now we got to move on to the next topic, which is indicators. Indicators change color at different pH values, right? Now, what's cool about this, right? Table M shows you the different types of indicators that's used in regions, all right? So how do you use this? Well, they change color when they gain or lose protons, okay? So why would this be useful? Yeah, you don't have to write that, right? Here we go. So how do we use this? Phenolphthalein. You might have seen this in bio class. Phenolphthalein, when it's an acid, right? Ready? Phenolphthalein, right here. When it's an acid, what's a pH of an acid? Anything that's what? Below 7. So if it's below 7, you are what? On the left side of this set of numbers. Would you agree? Then what color would it be? It would be colorless. Everyone okay? So it'd be colorless. If phenolphthalein is in a base, that means what? pH is what? Higher than 7. So we would be on that side, right? Then it would be what color? Pink. Now, it is this easy and it is also not this easy. Why? Because what's the next question somebody's going to come up with? Mr. Kim, that makes no sense because what if the pH is what if the pH range is what? 8 point. Look at the numbers, man. 8.5. What is it then? Is it colorless or is it pink? It's both. Meaning what? It's like baby pink, slightly pink, right? It's water with a hint of pink flavor, right? It's tiny pink, not black pink. That's not the K-pop. But anyway, so how does that work? That's why it's a little bit confusing. The way this works is this. With phenolphthalein, so if you have a solution, if you have water that has acid in it, you put vinegar into water, then your pH is going to be what? Low. It's low, right? Acid. So if you take phenolphthalein, which is in a dropper, it's a colorless liquid, you go blip, blip, put 2 drops in it. What color change would you see? Nothing. That's why it's so boring. And then what you do to that? You start adding some base, sodium hydroxide. At a drop, it goes from pH 2 to pH 3. What change do you see? Nothing. Add more drops. Keep adding. Now you go to pH of 4. What do you see? Nothing. It's the most boring thing ever. Keep adding more. You go to 5. What do you see? Keep adding. And now it's been 10 minutes. You've been adding. You're like, oh, God, this is so boring. What do? Jonah or Jeet is going to dump the entire beaker of base into the thing. And now what are you? You're at pH 13, which means you're going to be what? Right? That's literally how every titration acid-base experiment works. That's why we're doing virtual lab. Because what happens when you do that, you're like, oh, Mr. Kim, I screwed this up. Oh my God, you're gonna have to do it again. But we just spent 20 minutes. Okay, set it up again. Clean everything up, set everything up. You start adding. And after what? 25 minutes, you're like, dang it, it's still not turning color. Let's just dump it. You screw it up again. You're thinking, Mr. Kim, how could anybody be that stupid? Every year without failure, it happens. So, what does that mean? How does it actually work? You go to pH what? 7. What color? Colorless. You keep adding more. 7.5. Nothing. You keep adding. You go to 8. What is the color? Still colorless. That's what's so frustrating. And you keep adding more. You get pH of 8.1. What do you get? Yeah, see, if you get one of those where what's going to happen is now Kevin is going to be like, hey, look. And Kevin goes, oh, look, I think it's pink. People are like, no, it isn't. Yes, it is. No, it isn't. Yes, it is. And then what are you going to have to do? You're going to have to take a piece of white paper, right? Put it on the back of the beaker. And then you look at the color of the paper, color of the water. And he goes, look, it is just slightly pink. And they're like, no, man, it's not. And it's like, fine. You add a little bit more base. And what happens now? You're pH of 8.3. At which point, Kevin says, no, I do see pink, right? It's kind of like water with like a little pinkness to it. And people are like, I still don't see it, right? And you keep adding and you go to 8.5. And then what did they say? Oh, now it's a little bit pink. And Kevin's like, bro, it was pink a while ago, right? No, I see pink now, right? And you go to 8.8. What do you see? Now it's a darker pink. Everybody assumes it's pink, right? How do you know when you get to the end in the 9? You don't. Because it just gets darker. And when you get to pH of 9, right? Kevin's like, that's really dark. I think it's pH of 9. But then all of a sudden somebody's like, no, man, I think we can add a little bit more, right? So this is why indicators are terrible. This is why, if you have anybody have a pool or aquarium or a hot tub, right? You have those indicator things to check the water, the pH paper. How accurate are those? They're so inaccurate. That's why I love when I have a hot tub, right? I didn't buy it. It came with the house. I take the water into Leslie swimming pool and White Plains and then to get the water tested. I just want to test for other things like chlorine and all that stuff, right? But they'll take the water and they break out their pH test kit and then they go dip. And then they look at the color like, oh, your pH is a little bit off. And I'm like, are you serious? Trying to use that? Because what did Mr. Kim use? I use a pH meter and actually run a titration experiment. Right, on my aquarium and my everything, right? So understand how to use this. All you have to know is this, right? Another way they could ask you a question is, if a liquid that you have unknown liquid, you add methyl orange, and it turns red. What is the possible pH? Anything that's what? Done. Got it? Everybody got it? Yes? You understand that? Another one. Susie has a unknown liquid. She adds methyl orange and it turns yellow. Okay? And then she adds phenolphthalein to the same liquid and it stays colorless. What is the possible pH range? Yeah. So ready? Let's go break that down, right? So if Susie has, I should find out what the eraser button is. But okay, if Susie has a liquid where methyl orange turned yellow, that means it's what? Greater than 4.4. Everybody agree? So it's greater than 4.4. But when she added phenolphthalein, it stayed colorless, which means it is below 8. Do you see that? And then it says, in your booklet, write a possible pH value. Yeah, it's in the middle of those two. So what's a good number? 4, 5, 6, 7, 8. I don't know. 6, right? Everybody? Could you write 4.415? Yeah, but you're just being an ass at that point, right? You could, right? But any number between 4.4 and 8.0 would work. Would 7 work? Yes. Everyone understand that? If this is a multiple choice question, though, it's interesting because why? Because if they ask you, right, that and which of the following is a possible pH, right? How much are you going to bet that some of the values are going to be what? Less than 4.4, and some of the values are going to be higher than 8.0, right? So essentially, when you get to that, it goes, Susie has a liquid where it is yellow with methyl orange. Immediately, I look at the questions and I see a 4.0 and 2.0. What do I do with those? Cross it out. And then it says, but it's colorless in phenolphthalein. What are you going to cross out? Anything above 8. And guess what? I see a 13, so I'm going to cross that out. Hey, I'm left with one answer. I'm done. Right? Everybody okay? No, you don't seem okay. Are you okay? All right. Guys, man, I took off my sling for this, man. Come on. I hope you appreciate. I don't take off my sling until like Thursday at least, because I'm telling you, right? It's like one of those what is that in video game? Like you can use it, but like it uses up the energy and it doesn't build back up, right? It's one of those. I don't know what I'm talking about, right? You know what I'm talking about? Like in those like shoot 'em up games, you do that and it slows down things so you can dodge bullets, but it runs out the meter, right? That's my arm. All right. Remember, the numbers tell us when it changes color, methyl orange. All right, so we all know this, right? Right? So what are between 3.1 and 4.4? Regions, knock on wood, will never ask you a number in between the two. So regions will never give you like a pH of it'll say Susie has a pH has a liquid that is a pH of 3.89. What color would it be in methyl orange? They would never ask you that, right? But if they did, you'd say somewhere between red and yellow, right? Which is what? Like tangerine orange, right? Or let's say blood orange tangerine. Or like, no, they're never going to ask you that, okay? What they could ask you is, if Susie has a liquid that has that is suspected to be a pH of, let's say, 4, what's a good indicator that she can use? Right? Or they'll say, what's an indicator that she shouldn't use? Methyl orange wouldn't tell you anything, right? Everybody agree? That's another way they could ask you, right? Oh, it's another. Bromcresol green. Could you use that? No, it's right. So what's a good one to use? You can use bromthiamine blue, phenolphthalein, litmus would be terrible. Litmus, you can use it, or thiamine blue, right? So if they give you like again, if they give you another one where they say, would bromcresol green, if Tommy has a liquid and a pH turned out to be 4.0, right? Would bromcresol green be a good, and Tommy says that they can use bromcresol green to indicate the pH. Do you agree or disagree with the student and explain? And you say, no, I disagree with the student. Explain. Because he's stupid. No. You say, because why? because the pH value falls within the range and therefore it doesn't work. pH acid-base indicators only work if the pH you're looking for is outside of the range that you're trying to find. Got it? That's it. All right, strength of acid and bases, right? Moving on. Strength of acid and bases is not covered in regions. It's in your textbook, weak acids versus strong acids, right? So if this is another one of those that if you're really into it, right? First of all, a weak or strong acids are not covered in regions. It is supposedly, it's one of those where it's not covered in regions and it's also not covered in AP Chem. So where the heck does it get covered? Technically, you're supposed to cover it in honors chem and then arrive to AP Chem with it, right? But if you don't come from honors, that's why for region student going to AP, it's a lot of work for you because you got to read up and teach yourself on the few topics that honors supposedly covers. Luckily for this year, honors didn't cover it, right? Which meant that we had to cover it. That's why AP was so behind this year, right? But strength of acid and base is not covered in regions. So therefore, weak versus strong acids not really covered, right? Although one thing I do want to talk about is this, that I kind of skipped here accidentally, which is this, acetic. Is it polyprotic? All right. So let's take a look at this for a second. All right. Now you could go to the table and look it up, but acetic acid, also known as ethanoic acid, right, is HC2H3O2. All right. When you look at this, how many hydrogens do you see in this formula? 4. Well, why didn't they write it as C2H4O2? There's a reason why. Because, first of all, yeah, I think we did, right? But this one is a hydrogen in the front. Most likely, that's an ionizable hydrogen. So if you say, okay, maybe if that falls off, then the question is, then what are we left with? C2H3O2 minus. Is this a thing? How do we know? Well, guys, take a look. This is a what? Polyatomic ion. Do you see that? It's polyatom, polyatomic ion. Is it in the chart? Yes. So I know that's a thing, which means this is legitimate. So this does happen. Okay? This does happen. So what? The question is, why doesn't this act like a polyprotic? Well, if it acts like a polyprotic, what does that mean? Just like HSO4 minus, then we would expect it to go through one of these, right? C2H what? 2O2, 2 minus, right? I have a question for you. Is this a thing? No, it's not a thing. So therefore, this whole thing, it doesn't happen. All right. Now, if you remember, long time ago when I introduced table E, right? Polyatomic acid. I said polyatomic ions, polyatomic ions are multiple atoms that are covalently bonded to each other, that as a whole group pretend to be an ion and have a charge, which means do covalent bonds fall apart in water? No, only ionic does, right? That's why polyatomic ions do not further fall apart into smaller ions. That's it. That's the end of the line for them, right? So that's why acetic acid is a polyprotic or monoprotic. It's monoprotic. Okay, that's why they write the formula like this. So if they say, which of the following is a polyprotic acid? A, HCl, 2, HC2H3O2, 3, H2SO4, 4, HBr, right? You see someone's going to read and goes, oh, Mr. I think there's a mistake. I see 2 acids with multiple H's, right? What am I going to tell you? Read it carefully, right? And you're like, God, I hate this guy, right? But I'm right? You can read it carefully. So acetic is not a polyprotic. Be careful with that, right? That's an advanced topic for regions, but that's okay. It's cool. All right, so let's move on. Titration is a technique used to determine the concentration of unknown pH. We're not going to cover all of titration. I'm going to give you introduction to titration. All right, so what is titration? Titration is used to figure out what the pH of something is, right? So for example, let's look at it this way. What if there's a train carrying sulfuric acid, H2SO4, or nitric acid, right? Headed to a battery factory, going through Ardsley, and there's a derailment, train falls over, the tank break open, and then pours all of its sulfuric or nitric into town of Ardsley. And it goes into the local lake. Mr. Kim, you're being oddly specific. Yeah, it actually happened in the news out in Midwest. A train derailed carrying nitric or sulfuric, and then the tanks broke open, and literally the entire town got covered in, right? Nitric sulfuric, which means what? If you step outside, what happens? You're melting into the ground, right? So what happens? It goes into the lake. And you're like, oh my God. So you walk over to the lake and you look. First of all, you can't even breathe because it's like vinegar times 1,000, right? The fume. But if you can handle the fume, you look into the lake. The lake looks beautiful. Why? It's clear. What's in it? Nothing. No algae. No nasty leaves. How about fish? What happened to all the fish? It's not dead. It's gone. Why? It dissolved. Right? To which you're thinking, wow, well, you know, other than the smell, it looks really inviting. It's so crystal clear. So what happens? You decide to go skinny dipping, take off all your clothes, jump in. What happens?
They're gone.
You're gone. What?
They're gone.
It's actually happened. Do you know that? This actually happened to a couple hiking somewhere. It was a natural spring, and then there was a sign that said, do not get in the water, hot spring. Do not get into this hot spring. What happened? Because a hot spring is how hot? It's hotter than boiling water hot. But this boyfriend and a girlfriend went and they said, hey, let's be naughty and let's go skinny dipping. There's nobody here because, you know, it's like off the beaten path, right? You jumped over the railing, right? So he took off all the clothes, jumped in, and then he started screaming and yelling because what did he just jump into? Boiling lake water, at which point the girlfriend tried to take him out, but when she stepped her foot into the lake, she burned her foot. Stepped back, couldn't reach him, so she turned around, ran back to the town or the resort to get help. When they ran back, what happened? Boyfriend's gone. Why? He dissolved into the lake. Why? It also turns out that the lake was highly acidic. It was boiling acid that this dude jumped into. So what happened? By the time they came back, what did they find? Nothing. Bones? Nothing. There was nothing left. It's a clothes, right? So, problem. You wouldn't want a lake like that in Ardsley. So what do you have to do? So then what happens? They call the authorities, and then what happens? Black Hawks fly in. Kevin steps out. He works for the Army Corps of Engineers. Yes, he's a soldier, but what is he? He's a scientist soldier, right? So what does he do? He's got to figure out what he needs to do. So what happens? He'll suit up, take a little test tube of the lake water, take it back to his mobile lab, and run titration, at which point, using titration, he figures out exactly the concentration of the acid in the lake, and then he does a little bit more calculation, figures out how many dump truck worth of sodium hydroxide pellets needs to be thrown into the lake, tether it to a Black Hawk, have it drop into the lake, that bubbling reaction, and then what happens? You're done. Lake's cleaned up. It's just salt water now, right? That's cool, right? Is that what Army Corps engineers? Yeah, they actually do things like that, right? Environmental engineers. Here we go. Let me explain to you how it works, right? Works off the formula. Formula is easy. It's MAVA equals MOVBOV, right? And that's it. So we will continue going over how to use this equation tomorrow. I really strongly would like to try to get an assessment in before the week's out, because I really want to switch to a model where starting next week, I would, if possible, do regions review, finish up as next week. We're gonna have to do organic and nuclear, right? And after that, that should be like 2 days. After that, switch over to regions review. I want to do 2 things: regions review and just a bunch of virtual labs, right?
Yeah.
Right. Some of the virtual labs, I want to. I think I might even assign it for you to guys do it at home. But I want to really switch over to regions review, because I found out my wife's school, the chem teacher, he's already doing reviews, right? So I don't want to fall behind. Now, granted, compared to other chem teachers here, they're not in review mode yet, but honestly, That's my thing with my students. We go into review mode. Normally, I go into review mode in like first week of May. And then we literally spend all of May just doing nothing but reviews. I would like to do that as much as possible. All right. All right. So make sure that means tonight you're reading the textbook, you're reading the review book, right? And you're doing going over problems. Now, we covered most of the stuff for this unit except for titration, which means you should be able to do everything in the review book except titration. Got it?
What does titration look like? Like how does I take it up?
You have a long glass column that's like $500. You fill it with your sodium hydroxide. I'll explain it tomorrow. And you made it so you know the concentration and you know the volume. You take the beaker with the mystery lake water, but you put in the exact volume that you know. So you got a volume. No, oh, you don't know the concentration. So you know the volume. You don't know the concentration. You know the volume of the base because you made it, and you know the concentration because you made it. So you got one unknown. You got all knowns, and then when you put it in, when you get the peak of 7, that means the number of base and acid was equal because you're at 7, right? So then using those numbers, boom. Fine. Yeah. So what happens? You made the base, so you have the molarity. You have the volume because you took a specific amount from the lake, and then what you do is you start lowering the base in until you get to 7. But when it gets to 7, you stop. You know exactly how many volume that went in. That plugs in there. You're done. Okay. We'll do that tomorrow. All right. Have a nice day, folks. Bye. Bye. You too.